time to derive the equations that we need when dealing with batch-wise adsorption in a column. This is our breakthrough curve. The concentration changes with time, and let's choose a random time t and ask ourselves how much has been accumulated in the outlet, so how much has come out so far, and how much has accumulated inside the column. Now, if you want to figure out how much has come out, you need to take the flow times the concentration times the time. But our concentration changes all the time. So you can't just take C times T, but instead you need to take the integral of C dt. So F times the integral of C dt from time 0 to time t, that's the amount of material that has come out. Now C times T, well, you have C on this axis here and T on this axis here. So if C, for example, is in gram per liter and T is in minutes, then the unit of the blue area here is gram per liter times minutes. And if you multiply that with the flow, like in liters per minute, then you get grams, right? So F times the area under this breakthrough curve is the amount that has passed out in the outlet. So the blue area is a measure of how much has come out. Now, how much has accumulated in the column? Well, that must be the difference what has come in and what has come out so far. What has come in is pretty simple because the concentration in the inlet is the same all the time. So you just multiply F with C0 and the time that has passed. That's the amount that has come in. And as we reasoned before, this thing up here, that's what has come out so far. So if you take F C0 times T minus F times the integral of C dt from time 0 to time t, that is what has accumulated in the column. And we can rearrange that like this. F times the integral of C0 minus C dt from 0 to t. And you can rearrange that as well, and since C0 is a constant. But let's end with this one in the middle here. Try to remember that. Now, our next question is, what happens if we integrate all the way to T sat when we have reached saturation? Well, what has accumulated in the column then must be the same equation, right? F times the integral of C0 minus C dt from time 0 to time t sat. And that must be the area above this breakthrough curve. So the area between the concentration C0 and the breakthrough curve. Now, let's look at this as a geometric problem. This is an area, right? There must be some area here, a rectangle with the same area as this rather difficultly shaped thing here. So let's choose a time t star where the orange area here is the same size as the blue area, because then we can take this orange area and move it down here and cover the blue completely. This rectangle must have the same area as this area here. And we call that T star. And this is a quick way to get to the adsorption capacity of a column once you have the breakthrough curve. If, and only if, you have a symmetric breakthrough curve, then T star happens when the concentration is half of C0. Okay, how do I choose breakthrough point then? Because if I choose a breakthrough point, a breakpoint, then the blue area here is the capacity we have used, and the orange area here is an unused capacity, and then the thing down here is what has come out. if we choose this time early, the benefit is that we don't lose any product out to the outlet, or not much contaminant comes out in the outlet if it's the contaminant that we are adsorbing. But if we stop early, then we also have a lot of unused capacity, meaning that we need to use more adsorbent. A common breakpoint is typically somewhere between 1 and 5% of the C0 concentration. So, but that might vary considerably between different situations. We will talk about a degree of utilization, and approximately speaking, that is the length of the column times TB divided by T star. And the length of the unused bed is then 1 minus that. So L times parenthesis 1 minus TB divided by T star, to be more precise. And so, for example, if you have a length of unused bed that is 1 centimeter and the length of 10 centimeter of the column, then we have used 90% of the column capacity. This is a simplification. It relies on this area below the breakthrough curve, so how much has come out, to be negligible in comparison with the capacity at the breakpoint. And you can look in the compendium for more details on how that works.